The ideal gas law is a nice and simple model that helps us to understand how gas properties relate to each other. And it even works decently well to give us reasonable predictions under certain conditions. But the simplicity comes with a cost. The assumptions that go into the ideal gas law ignore physical realities that have real impact on real gases. So let's look at a quick example. What's the pressure of 55.55 moles of water in 1 liter of space at 298 Kelvin? So according to the ideal gas law, P equals nRT over volume equals 55.5 moles times 0.08206 liter atmospheres per mole Kelvin times 298 Kelvin, all divided by 1 liter, gives us 1,358.4 atmospheres. That's almost 1,400 times atmospheric pressure, when the real answer is around 0.03 atmospheres, because real water undergoes a phase change into liquid. So 55.5 moles of water in 1 liter of space is just liquid water, or 1 kilogram of liquid water in 1 liter of space. So what would happen if we tried to double the amount of water in the same amount of space? According to the ideal gas law, we could just double the pressure to about 2,700 atmospheres. That's the linear relationship laid out by the equation that assumes that the atoms and the molecules themselves take up no space at all. In reality, each water molecule takes up a little space, and if we tried to compress twice the water into the same amount of space, doubling the density, we'd be pushing the atoms so close together that we're no longer talking about particles impacting the sides of the container, but the electron-electron repulsion of something like 2 times 10 to the 26 atoms, generating way more force than what's accounted for by the ideal gas law. So the first correction we have to make to the ideal gas law is to have it account for the space physically occupied by the molecules, space that has to be excluded from the usable volume of the container. We can do this by introducing a new constant B in units of liters per mole, the volume taken up by 1 mole of the actual gas molecules, and multiplying that by the moles of gas. The second correction has to account for the attractive forces that cause the molecules to aggregate into fewer, larger particles. For instance, the liquid water in this container acts more like one big particle in constant contact with the container walls than it does like 55.55 moles of particles periodically striking the container. The pressure exerted by a gas on the walls of its container depends on both the frequency and on the force of the collisions between the gas and the container walls. Since both frequency and force are functions of the molar volume, or moles per volume, N over V, what we're looking for is something that is a function of the square of the molar volume to account for both the frequency and the force. We do this with a second new constant, A, as a moderating factor for subtracting the molar volume twice, one for the reduction in frequency and once for the reduction in force. Because this second term also has to have its units in pressure, the constant A therefore has units of atmospheres times liter squared over mole squared. What we've written here was first developed by Johannes van der Waals and is called the van der Waals equation of state. The two constants A and B are the van der Waals coefficients. These modifications to the ideal gas law remove some of the simplifying assumptions, making it more complex, but also making it more true to reality and better able to predict actual states of real gases. It also means that we need to find values for B and A, values that dictate the relative repulsive and attractive forces present in a particular gas. These constants are determined experimentally, and for our purposes, we mostly just look them up in a reference table. Even though this is an improved model for gas behaviors, there's no reason for us to assume that it's perfect or that it's universal. So it's always good practice to think about the model's limitations, to try to find where it works best and where it starts to break down. First, let's see what happens if we start to expand the volume towards infinity. In the first term, if volume is huge, then subtracting any number nb will have almost no effect. It's completely negligible and we can ignore it. In the second term, as volume gets larger, the term as a whole gets smaller. And at the limit of infinity, this term goes to zero, and we end up recovering the ideal gas law. Now this is useful because it tells us that when the volume is large, or the number of moles is small, we can apply the simpler ideal gas law, and when conditions are more realistic, we need to apply the more accurate but more complex van der Waals equation. Next, if we apply the van der Waals equation to a gas at a bunch of different temperatures and volumes, we would find some strange behavior for pressure when the two terms, the repulsive term and the attractive term, are on the same order of magnitude, or their values approach the same number. That condition suggests that the attractive and repulsive forces are balanced, and so it acts more like a liquid than it does like a gas. That point is called the critical point, and while it does create some difficulties for this equation, it also gave Johannes van der Waals another good idea about gas behavior that we'll talk about next time.